The last part of the algebraic limit theorem is that the limit of a quotient is the quotient of the limits, provided the one in the denominator is non-zero. So we're actually going to prove something that's slightly simpler, but together with our previous result about the limit of products, it finishes off the proof. So if we can show that reciprocals work the way we think, that the limit of a reciprocal is the reciprocal of the limits, then we get quotients by just taking, say, 1 over a sub n multiplying by bn. Right, so I'm calling this the fourth property of the algebraic limit theorem. It's a slight modification, but together with property 3 does the trick. And it's a little easier algebraically. So we start with an epsilon bigger than 0. That's our standard start. Consider the thing that we have to make less than epsilon, and do some algebra to reveal something we know we can control. So if I do this algebra, then inside I'm going to get L minus AN over ANL. And that's the same as absolute AN minus L over absolute AN times absolute L. And we want to make that less than epsilon. Now, this one presents a new challenge that the previous ones didn't. Right? We've had some trouble before where we had a term like a sub n appear, and we had to get a bound for it so that our epsilon didn't depend on n. But this case is actually a little bit more problematic, because not only do we need a bound for a sub n, what we really need to do is bound it away from 0. Right? So if we think about this in the denominator, the problem that it presents when we're trying to make the whole thing be small is that a sub n could get really, really close to 0, and that would blow up the quotient. So we have to somehow make sure that the a sub n here in the bottom can't get too small, right? So that's what I mean when I say we have to bound it away from 0. And we're going to use a property related to the triangle inequality to do this. This was from exercise 1.2.6. I think it's part D in that exercise. That's what we're going to use here in just a moment. So although we don't know necessarily right off how we're going to bound a sub n away from 0, we do know, because a sub n converges to L, that we can make it get as close as we like to capital L. And that's kind of the trick for bounding it away from 0. And the idea is that, well, here's a picture for what we're going to do. It doesn't represent a proof, but let's say there is 0, and let's say our limit, which we know isn't equal to 0, that's an assumption. Let's say our limit is positive, then we can use the definition of convergence to make sure that past a certain point, all of the ANs are inside this interval. But if they're inside this interval, they can't get close to 0. So that's kind of the idea, right? So we'd have a sub n plus 1, and then those would continue. But the important point is, originally, we're going to make a choice here that gives us knowledge about how close the a sub n's can get to 0. So by definition, there exists some n1 such that n bigger than or equal to n1 implies that a sub n minus L is smaller than absolute L over 2. So I'm making a useful particular choice for epsilon, right? I know the definition works for all positive numbers, so certainly it works for this positive number, absolute L over 2. Now, once I know that, by exercise 1.2.6, absolute AN minus absolute L is smaller than plain AN minus L inside the absolute values. And so it is also less than absolute L over 2. So AN minus L is bigger than minus absolute L over 2, smaller than absolute L over 2. And now I can get AN by itself by adding absolute L to both sides. And I get absolute L over 2 on the left and 3 absolute L over 2 on the right. But this is the piece that's important. Right? With this particular choice of epsilon, I have guaranteed that A sub n can get no closer to 0 than absolute L over 2. And that's going to let me finish off the proof as follows. So by definition, there exists capital N2 such that if n is bigger than N2, then we get A sub n minus L is less than epsilon times L squared over 2. Now the reason that turns out to be the right choice is back here. I've got A sub n minus L on top, and on the bottom something that's no smaller than absolute L over 2, and so together these things are no smaller than absolute L squared over 2. And when I plug in or bound the A sub n minus L by this, the L squared over 2's cancel. So to finish this up, I get, let's take capital N to be the larger of the two individual capital N's, then N larger than capital N implies that the thing I had left off with, A sub n L, is less than epsilon L squared over 2 all over absolute L over 2. Right? So I've made A sub n as small as it can get, which makes the fraction larger, and then that absolute L is still there. All of that cancels. So that is my epsilon as required, and that completes the fourth part of the algebraic limit theorem, and therefore the entire algebraic limit theorem.